Okay, let's now look at transmission, and specifically we're going to be looking at the electrical distribution system. We're going to be looking at this exclusively through an AC lens and talking about the downfalls of DC in this application. I will just point out though that is a slight oversimplification, and DC technology has been increasing in its efficacy and use, but if you're interested, please let me know. I can give you some resources about that. These style of questions, we need to be able to do a few things. Number one, we're looking at this through the lens of transformers. We're going to be looking at how we can actually use a transformer, or multiple transformers, I should say, to reduce power losses. That's the main purpose of what we're looking at here. We're going to be looking at losses across transmission lines, so that's going to be through the lens of power losses and voltage losses. Remember, power is just talking about energy per unit time, and voltage is talking about energy per coulomb. So they're both a measure of energy losses to the environment. Remember, not lost, just transformed into an unhelpful form. We're going to be looking at the advantages of using AC power, and you're probably going to guess that's got to do with the fact that we can use transformers with them. So there's two main style of question I see with this kind of thing. Calculation questions, which you're probably going to be quite strong at so long as you look at some of the tips and tricks that I talk about, but there's also some explanation style questions which can be hard to earn marks on if you're not really specific with your terminology, so let's explore some of them. To get ourselves going, let's look at the really basic design of a really poorly designed transmission system. So just say we've got an AC power supply, and that could be modeled as some sort of, power plant, coal, nuclear, could even be like wind power or something like that, hydroelectric. And we've got it across some transmission lines here. Now, those transmission lines are evidently not drawn to scale because we know there are kilometres and kilometres of transmission lines all across our neighbourhoods. We're not all right next to a power station. And we're going to be looking at that connected to different loads. So here we've got a house, that's the load. It could be a piece of machinery, it could be something in particular. So that could be drawn as a circuit like this. We've got our variable power supply, and we represent that with a circle with this through it, representing that it's a sine wave, or that AC curve of current and voltage that we've been looking at. Now, those transmission lines, we cannot assume, like we have with circuits in the past, that they are zero resistance. We need to assume that they do have resistance, especially if we've got kilometres or even meters of wire. We're going to have a non-negligible amount of resistance. So we do need to take in that into account, and that's what's going to cause those voltage and power losses. Then we're going to have some load. Now, we're going to model that as a series circuit. Sometimes they give the resistance of individual power lines, and sometimes they give a combined resistance. So we'll explore some of those questions. And some really important stuff here. We're going to be using this terminology. V supplied, or we could even talk about V supplied. I think I said V, but I meant to say P. The supplied voltage and the supplied power, that is what the power plant, or what was originally put into the system. Now, we are going to have an unhelpful voltage drop. We could also have an unhelpful P drop, power loss. They're both a measure of energy. So that's unhelpful. That is power or voltage that's lost to the environment, never to be seen again. Really unhelpful, don't want it. That means that V load, or even P load, I'm trying to do this with one take, can you tell? P load or V load, that is the useful voltage out. That's what's not been lost. And hopefully you can see whatever is supplied minus whatever is the drop is going to be what the load actually gets. That's really important. You need to be aware of these three areas here: the supplied voltage or power, the dropped voltage or power, and the load voltage or power. That is critical, and that's where most people make mistakes. So in the little red box here, mention something that I mentioned before. Resistance of two transmission lines must be treated as a single resistance unless specified otherwise. If we had, for example, instead, I'm going to erase this, so don't put this on your sheets, just say we had two resistors. That's the old-fashioned way of representing a resistor, just so you know. There's two ways, the box or the zigzag. Those two resistors would be in series, and in series we add resistances. So R series, if we called this 1 and 2, it'd just be R1 plus R2. In parallel, it's a little more complex, but in series you just add them together. So that's what this is talking about here. Sometimes exam questions will provide the resistance of each of the wires in the transmission line separately. We use the total resistance, which is the sum of the resistances of each wire because it's in series. And that will help us calculate the voltage drop and the power loss. We don't tend to call it P drop. Maybe I'll go back on that. We tend to call it P loss rather than P drop. We tend to talk about voltage drops rather than voltage losses. It's just a terminology thing here. So let's go with P loss, which looks like plus. So we'll go with P loss here. The resistance of the transmission lines causes a voltage drop in the lines. Now, how can we calculate that? The voltage drop, which we mentioned before, that can be found using two quantities. The current in the line, I line, and the resistance in the line, R line. So current in transmission lines, resistance in transmission lines. That's not too bad. Now, in a simple transmission system without transformers, the voltage that's delivered to the load will be the difference between the voltage supply and the voltage drop. So like I mentioned before, whatever voltage we measured across the load, the useful voltage out, that had to be the supplied voltage take away the dropped voltage. Now, the power loss due to the resistance in the transmission lines can be calculated in two ways, but you must be extraordinarily careful. P loss, like I mentioned before, rather than P drop. That is the current in the line that we had again, but this is V drop. This is the voltage lost due to power lines using it. That's possibly a clumsy way of writing it, but we're talking about the power lines themselves. Due to them having a resistance and a current means there's a voltage going to be dropped across them, like any resistor that has a resistance and a current. We could also calculate that using I squared line R line. So what do I mean be careful with this? Often people, when they're calculating P loss, instead of V drop, they use V load instead. And V load is not the voltage used within those lines. So you need to be really careful, and I'll scaffold that when we get to some questions a bit later on. But it is really important to distinguish the two. So power delivered to the load will be the difference between the power supply and the power loss. P load is going to be P supplied minus P loss. Exactly the same equation, but for power instead of voltage. Now, this relationship also applies when transformers are included, but you're going to see that the power losses are going to be smaller. And we'll talk about why soon, but let's look at a really bad example of a transmission system, one that doesn't have transformers, and I promise we'll talk about why transformers are going to make it better soon. So we have a generator. It's AC generator. We could also call that an alternator. That could be a petrol generator. Obviously, there's not someone hand cranking that in there. Now, it's producing 200 watts. And, oh, that's nice, 40.0 volts RMS. So they haven't given us a peak or a peak to peak. They've given us the RMS value. That's really nice. Which is used to supply a food truck. The food truck here is the load. The transmission lines each have a resistance of 1 ohm each. So that means the total resistance is going to be 2.00 ohms because we can model this as a series circuit. Calculate the current in the transmission lines. Okay, a few things here. Do we know V drop? It is not 40 volts RMS. If that were the case, then the food truck would have absolutely no voltage provided to it at all. So at the moment, we don't know what it is. So we can't use V equals IR to be able to figure out that current. Okay, so we are going to need an alternate approach. Now, I've noticed we know the power and we know the voltage supplied by the generator. So we could use P equals VI, and that would tell us the current that's supplied to the circuit. That would be great. So P equals VI, and we're looking at the generator. I could use subscripts of G everywhere. I'm just going to write G for generator. If this were in the exam, please write generator. Okay, so current is going to be P on I. Now remember, for power calculations, we always need the RMS value. So we already have this, but this is a useful note to our future selves in case they provided us with a non-RMS value. You've probably seen the mistake that I made. I should be writing I equals P on V. There we go. Okay, so current equals the power, which was 200 watts, and the RMS voltage was 40.0. So we need to give this to 3 sig figs, so 5 amps here. Cool. Okay, so we now want to figure out the voltage drop across the transmission lines. Now we know the resistance, we know the current that's provided by this AC, the current in this circuit is going to be the same at all points. There's nothing to change the current. So that means V drop, that's going to equal I line times R line. So the current in the lines is the same as this, I line. So 5.00 times that resistance, 2.00. So 10.0 to have 3 sig figs at the end. Really nice. Calculate the power loss in the transmission lines. So P loss. Remember, we didn't write P drop. It was P loss. So PLOS equals I line squared times R line. That looks a little bit funny. So we had the current in the line was 5.00 squared. The resistance in the line was still 2.00. So 5 squared is going to be 25 times 2. That's going to be 50. We need 3 sig fig watts. Okay, there's other ways you could have calculated this, by the way. P loss. You could have also done V drop times I line. So the voltage drop in the line was 10 volts. The current in the line was 5 amps. So that would also have given us 50.0 watts. So 2 ways we could have done that. Is there another way we could have done it? Oh, we had that other equation for power. Remember, we also had P equals V squared R. So we could have P drops V drop squared over R. So V drop would have been 10.0 squared over R. Resistance was 2.00. So that also would be 100 divided by 2, so 50 watts. Now, we want to figure out the voltage delivered to the food truck. My suggestion would be V supply minus V drop equals V load. V load. Okay, so the supplied voltage, we had 40 volts. The lost voltage across the line was 10 volts. That's a huge loss. So that's going to give us the 30.0 volts is actually getting to the food truck and supplied. So that's pretty crazy. We had 40 volts that was supplied, 10 volts dropped, only 30 volts. That's a 25% loss of voltage. That's pretty bad. Okay, V power. So V, sorry, not V power. Power of the load equals the power that's supplied minus the power that is lost. I think we just said P loss. Okay, the supplied power was 200 watts. The lost power, we calculated that in many different ways, but it was 50 watts regardless. So we only have 150 watts, that's 3 sig figs, remaining. That's a real shame. That's 25% power loss. Don't know about you, but I really do not want to be losing that much power at every time. Just so you know, you could have also done the voltage drop across the load by figuring that out. We figured that out here. We had that 30 volts, and you could also use the current across the load. So you could have done P load equals I I load V load. Current in the load was the same as the current throughout the circuit, that 5 volts. Amps. And the voltage across the load we figured out was that 30, and that would also give us that 150 watts that we needed. So 25% power loss or a 25% voltage loss is pretty crummy. So we need ways to not lose as much power. Imagine if your electricity bill, whenever it came in, you were wasting 25% of it just getting it to your house. Because they would still charge you on what they supplied you, not what you eventually got. Because P loss equals I squared line times R line, we can actually reduce the power losses by. So, number one, we could shorten the wires. So shorten the lines, less wire would be less resistance. Now the problem is this isn't practical. We can't have a power station near every single house to reduce the distance between the power source and the load. So as much as that would be a lovely idea, I don't particularly want a coal-fired power station right next to me. A wind farm would be pretty cool, but I don't think everyone would love having wind farms right next to every single house. We could also increase the diameter of the wires. You might recall from last year, resistance was equal to something called resistivity times the length divided by the area. So a larger area would lead to a smaller resistance. Also, like we just spoke about, shorter length, shorter resistance, smaller resistance. Also not practical. The problem is our power lines, they cost money to produce. And also, if you have a lot of metal within them, that's a lot of weight. So it'd be a larger amount of material. So the final thing that we could do is we could actually decrease the current. Now, this is actually possible, and this is very doable by using transformers. So, transmitting at high voltages and low current reduces power losses. This actually requires us stepping up the voltage at the power station and stepping it down again for industrial or domestic use. So remember when we looked at transformers, when we stepped up the voltage, that was in a step-up transformer, so going from a small number of coils to a large number of coils. Because we have the same power on both sides of the transformer because we're looking at ideal ones, the consequence of that is that the current went down. So increasing the voltage, the purpose of that is to make use of the fact that the current has the inverse relationship and will reduce by the same factor. That is going to be the big thing here. Okay, so how's that going to look? That means from the power station, shortly afterwards, we're going to put in a step-up transformer. Yes, I know my drawing is fantastic. So step-up transformer will increase the voltage and it will decrease that current. Then we have our transmission lines. I'm going to draw a resistor within here just to visualize the fact that the transmission lines, because they're so long, they have to have a resistance. Then we need to step back down that voltage so it's usable. We don't want 10,000 volts going into people's homes. So we would then have a step down transformer, not necessarily the same, but it could be, going to the load, and I'm just going to awkwardly draw it like that. So here, the voltage would be stepped down, the current would be stepped up again. So why did we do this? Increasing voltage means current is decreased due to same power, primary and secondary transformer. Why was that useful? A lower current, so current being lower, leads to, so this leads to V drop being lower, and therefore P loss also being lower. That's the whole point of what we're doing. And for P loss, remember P loss equaled I squared, so I line, R line. So current squared, remember if we're squaring something, it has an even bigger impact. So reducing that current really reduces the power loss. Down at the end, so step down to be a usable, I think I misspelled that, voltage. Nice. So remember, power is not actually lost in the transmission lines, it's transferred. So it's degraded into heat, which is unusable and unhelpful. The power supplied to the consumer is equal to the power supplied at the start minus the power loss in transmission. So it's still that P load equals P supplied minus P loss, or V load equals V supplied minus V, you could say drop or loss. I really don't mind. So I think I'm going to pause it there. We're going to do the exam questions in a separate video because I've realised this one has gotten oddly long. Not really sure why. I think it's because I waffle. See you soon.